How does the quantum Fourier transform enable phase estimation? Imagine trying to find a hidden pattern in a sea of numbers. Now picture doing this with quantum bits instead of regular ones. That's what the quantum Fourier transform helps us do in quantum computing. It's like a super efficient way to decode the secret language of quantum states. When working with quantum algorithms, especially for finding eigenvalues, this transform becomes a game changer. It turns complex phase information into a form we can measure easily. So how does it work? Let's break it down step by step. First, the goal of phase estimation is to find the phase, which is a number between 0 and 1. This phase is part of the eigenvalue of a unitary operator, which is a fancy way of saying a special kind of mathematical function that preserves certain properties. We start with an eigenstate, a quantum state that has this phase attached to it. The challenge is to figure out what that phase is. Next, we prepare a quantum circuit with two registers. The first register, called the estimation register, begins in a superposition of all possible states, thanks to Hadamard gates. The second register holds the eigenstate, which contains the phase we want to find. Then, controlled operations are applied, where the first register controls powers of the unitary operator. These controlled operations encode the phase into the quantum state's amplitudes, or how likely the state is to be measured in a certain way. Now, here's where the quantum Fourier transform comes into play. After encoding the phase, the first register is in a superposition where the phase information is hidden in the relative phases of the quantum states. The quantum Fourier transform acts like a magic decoder. It takes this superposition and transforms it into a new state where the probability of measuring a specific binary number directly relates to the phase. Essentially, it concentrates the amplitude on the basis state that best approximates the phase. Applying the quantum Fourier transform is efficient. It uses a sequence of simple gates, like Hadamard and controlled phase rotations, and only needs about the square of the number of qubits in operations. This efficiency is what makes quantum computers so promising for these tasks, especially compared to classical methods that would take much longer. Finally, when you measure the first register after applying the quantum Fourier transform, the result is a binary number that closely approximates the phase. The more qubits you use, the more precise your estimate becomes. This process is at the heart of many quantum algorithms, like factoring large numbers or simulating molecules, where knowing the eigenvalues of certain operators is key. In short, the quantum Fourier transform turns the phase information stored in a quantum state into a form that can be read out with a measurement. It's like translating a secret code into a language we can understand directly. This ability to efficiently extract phase information makes it a cornerstone of quantum computing and many of its most exciting algorithms.